Welcome to the Curious Culture Club, where we explore the wonders of our technological world. Today, we delve into the marvel that is quantum computing. It's a leap from the familiar world of classical computing, where data is processed in binary bits, ones and zeros. Quantum computing introduces us to quantum bits, or qubits, which can be both 1 and 0 at the same time, thanks to a principle called superposition. Quantum computing thus marks a significant departure from the classical computing paradigm. To fully appreciate the quantum revolution, we need to understand the limitations of classical computing. It all started with the invention of the transistor in the mid-20th century, a milestone that catalyzed the digital age. This was followed by the development of integrated circuits, which allowed for the miniaturization of electronic devices and the birth of personal computers. However, as we've advanced, the limitations of classical computers have become more evident. They operate on bits, processing data in a linear fashion, one bit at a time. This makes tasks with high computational complexity, such as simulating molecular interactions or cracking cryptographic codes, extremely time-consuming if not impossible. Additionally, we're nearing the physical limits of miniaturization, as transistors can't be made infinitely small. This has led to a plateau in processing power, known as Moore's law slowdown. The shortcomings of classical computing have paved the way for a new computing paradigm, quantum computing. The world of quantum computing, while complex, holds immense potential. Dive into the heart of this potential, and you'll find principles that are as fascinating as they are revolutionary. The first of these is superposition. In classical computing, a bit is either a 1 or a 0, on or off. But in the quantum realm, a qubit, the quantum equivalent of a bit, can be both 1 and 0 at the same time, thanks to superposition. This means that a quantum computer can process a vast number of possibilities all at once rather than one by one. The second principle is entanglement, another quirk of quantum mechanics. When qubits become entangled, the state of one qubit becomes linked to the state of another, no matter how far apart they are. Change the state of one, and the other changes instantly. This can potentially allow quantum computers to process information faster and more efficiently than classical computers. But what really sets quantum computing apart is the concept of quantum supremacy. This is the point at which a quantum computer can perform a task that is practically impossible for a classical computer to do in a reasonable amount of time. Imagine solving a complex problem that would take a classical computer thousands of years in just a few seconds. That's the power of quantum supremacy. Yet it's not just about speed. Quantum computers are also expected to drive breakthroughs in areas such as cryptography, where they could crack codes that are currently unbreakable. In optimization, by finding the best solutions to complex problems. And in simulation, by modeling phenomena in the natural world that are beyond the reach of classical computers. These properties set quantum computing apart, promising unprecedented computational power. The journey towards practical quantum computing has been filled with milestones and challenges. Notably, the development of the first quantum bits, or qubits, marked a significant stride in the race towards quantum supremacy. These qubits, unlike classical bits, can exist in multiple states simultaneously, offering the potential for exponential computational power. Yet, the path to a scalable quantum computer isn't without obstacles. Quantum systems are incredibly sensitive, requiring near absolute zero temperatures and isolation from external noise to function accurately. Another hurdle is quantum error correction, which is essential in maintaining the integrity of qubits during computation. To overcome these challenges, researchers across the globe are exploring innovative solutions, from topological qubits that are inherently resistant to errors to quantum algorithms that minimize computational errors. Despite these challenges, the quest for scalable quantum computing continues, fueled by its potential to revolutionize numerous fields. The future with quantum computing is not just about faster computations. It's about redefining the boundaries of what's possible. Picture cryptography, where quantum computers could decrypt anything encrypted by today's standards, redefining security. Envision optimization, where logistics, supply chains, and even global economies could be streamlined with quantum algorithms. Imagine simulations, where complex systems like weather patterns, Biological processes or entire galaxies could be accurately modeled, opening up new avenues in scientific research. These applications are just the tip of the iceberg. Quantum computing has the potential to disrupt virtually every industry, from healthcare and finance to space exploration and artificial intelligence. It promises a new era of discovery, innovation, and problem solving, where the once unthinkable becomes achievable. But remember, every revolution comes with its challenges. We're at the dawn of the quantum age, and the journey ahead is both exciting and uncertain. The quantum revolution is poised to transform our world, opening doors to solutions for problems once thought unsolvable. The potential of quantum computing is vast and exciting. Picture this: a world where complex problems are solved in microseconds, where impenetrable cryptographic codes are deciphered effortlessly, where simulations are so accurate they can predict the weather years in advance. This is not sci-fi, but the promise of quantum computing. The question is, which part of this quantum future excites you the most? How do you see it changing our world? Share your thoughts in the comments below.